In this video, I'd like to continue talking about the roots of complex numbers by looking at a more challenging example problem where we need to find the three solutions to the equation as seen here, where we are essentially finding the cube roots of some complex number here. And the general strategy for finding roots of various numbers is to rewrite each side of the equation in either its polar form or its exponential form and compare the two sides of the equation. Now, we will use exponential form since that tends to be a bit quicker. So let me just make a bit more room. And we know that a complex number z in its exponential form is the magnitude of the complex number multiplied by e to the I times theta, where this e to the I times theta, we can use Euler's formula. This is just the cosine of theta plus I times by the sine of theta, and this expression on the right-hand side, this is just the polar form. But we will use the exponential form since it is a bit more compact. Now, rewriting the left-hand side using this exponential form, we will have the magnitude of z multiplied by e to the I times theta, and everything is raised to the third power. And on the right-hand side, to rewrite it in its exponential form, we need to figure out its magnitude and its direction theta. Now, to do that, we will need the formulas. We know that to find its magnitude, we could plot this on the complex plane, draw a picture and a right triangle, and use the Pythagorean theorem, or we could just remember the formula that its magnitude is the real part squared plus the imaginary part squared. And the real part we know is this minus 4 root 2. We'll square that. The imaginary part is 4 root 2, and we will square that. We will add those together here. Now when we square 4 root 2, we square the square root, and that is just 2. They cancel each other out. And 4 squared is 16, so we get 32 here. And this will give us the same answer since negative times negative is positive. And when we add those together, we just get 64. And the square root of 64 is 8. So the magnitude of this complex number is 8. And its direction we can find by, again, drawing a picture or just using the formula that theta is the inverse tangent of its imaginary part divided by its real part, but we do need to be a bit careful. If we plot this number here, so it will have a magnitude of 8 and its angle will be this angle here, theta. But the issue with this formula is that it only outputs values between negative 90 degrees and positive 90 degrees. So when we get a value using this formula, we will actually get the angle down in the fourth quadrant. It will be this point right here, and we will have to add 180 to that to get the correct angle. If you want to use a different method, you can use this picture here. You can draw a right triangle, find this angle, and then use geometry to figure out this angle right here. You can take 180 and subtract this angle on the inside. But using the formula, we just need to be aware of what quadrant we're in and either add or subtract 180 to that. So if we plug in our values, we get that theta is the inverse tangent of the imaginary part, 4 root 2, divided by the real part, which is minus 4 root 2, which simplifies to the inverse tangent of negative 1. And if you evaluate this, either on the unit circle or with a calculator, you find that theta is negative 45 degrees. But since we know our angle is in the second quadrant, we found this angle down here, we will have to add 180 to find the correct angle. And when we do that, our angle will be 135 degrees, or we could do this in radians if we want, but we can keep this in degrees. So with this information, we can rewrite this complex number as its magnitude of 8 multiplied by e to the I times by theta, which is 135 degrees. But we also have to consider the multiples of the angle, since every time we add 360, we just go all the way back where we started. So if we add 360 multiple times, we can multiply it by some integer k. This will account for all the possible angles that are equal to 135. And for these integer values, we really only need 3 since there are 3 solutions. So we can use 0, 1, and 2. But if you want, you can use any other 3 values in order. We can use the negatives or numbers higher. It's just if we use more than 3, then we end up with duplicate solutions. And if we simplify the left-hand side of this equation, we are cubing everything. We get the magnitude of z to the third power multiplied by e to the I times by 3 theta, an exponent to an exponent we will multiply. And this is equal to this expression here on the right. And for this equation to be true, we know that the magnitudes have to be equal, and we know that the angles have to be equal. And let's start with the magnitude. We can say that the magnitude of z to the third power is equal to 8, and we can take a cubed root of each side or raise each side to the 1/3 power to find that the magnitude of our solutions has to be 2. And likewise for the angles, we say that this angle here of 3 theta has to equal this angle here for this complex number of 135 degrees plus 360 degrees multiplied by k. And we can divide everything by 3. So that theta is 45 degrees plus 120 degrees multiplied by k. And our next step is to find the different angles of our solution. So let me make some more room so that we can continue this problem down here. And if we look at theta 0 when k is equal to 0, we just get 45 degrees. If we look at when k is equal to 1, we add these together, we get 165 degrees. 45 plus 120 is 165. And we'll look at a third solution of theta 2. When k is equal to 2, we'll have 240 plus 45, which will be 285 degrees. But if we look at any higher values of k, then we will start seeing duplicate solutions. Since k equals 3 means we are taking 45 and adding 360 to that. But every time we add 360, we just end up back where we started. So if we looked at theta 3 when k is equal to 3, that's actually just equal to this solution. And any other value of k we plug in, we will just get one of these 3 solutions. So we have 3 solutions now where the magnitude of each of these is 2, and we have their various angles. So if we want, we can plot these now on the complex plane. We know that the magnitudes are 2. We have our imaginary axes and our real axes. And we will notice symmetry about the origin, essentially, on this complex plane. And let's plot these so that we can see that. We have a 45-degree angle, and its magnitude is 2, so that's somewhere right about there. We have a 165-degree angle with a magnitude of 2, which will be about there. And this is 270, so 285 will be somewhere right here. And you can test for the symmetry by drawing a circle about these points. And keep in mind, this is not to scale, so this circle isn't exactly right. But if we did draw this perfectly, all of these points will be on this circle, where the radius of this circle is the magnitude of each of our solutions. And there are various ways to test that this is correct. We can rewrite these in their exponential, polar, or rectangular forms, and then raise each of them to the third power to make sure that we do get back this value right here of minus 4 root 2 plus I times by 4 root 2. But I will just check one of them just so that you can see the process, and we'll compare it to its exponential form, this 8 times e to the I times 135. So we will rewrite one of our solutions in that form. Let's look at the case when k was equal to 0, so this theta 0. We have its magnitude, which was 2. We can call this z0. Its magnitude was 2, and its angle was 45 degrees, so we have e to the I times by 45. And we're going to take this number and raise it to its third power. So I'll just rewrite this expression, and raising it to its third power, since we have a product here, each factor will be raised to the third, and 2 to the third power, that is 8. And we have an exponent to an exponent, so we will multiply the exponents. We have 3 times by 45, and 3 times 45 is 135 degrees. So we check this first one, and it does make sense. And likewise, we could check the other two by this same process, but I will leave that as an exercise.